We'll start now with the keynote speeches, and then we'll have Ricardo here. Ricardo, please. Ricardo will be presenting instead of Valmir Freitas. Valmir Freitas had a problem, but they worked together. And then I asked Ricardo to present himself and also to say a few words about Valmir, and then he will make his presentation. Okay? So, thank you very much.
Okay, good morning, everyone. So I'm Ricardo. I've been working with Professor Valmir Freitas here at Unicamp for over a decade now. I finished my PhD, and myself with some other colleagues, former students from Professor Freitas, have founded this company, ERA Research and Energy, Research and Analytics. Our main area is to develop data analytics techniques more focused on the distribution systems on the power grid. So today I would like to bring a perspective on the power grid, what is energy transition and grid modernization, what is this causing in the power grid, and how utilities are having to adapt to it, right? And this is our main area of work at ERA. We develop techniques, data analytics techniques to work with the grid, with the systems, with the modern systems, with more control and more measurement, and also more power electronic based devices. So my idea here today is to present a little overview, some ideas, what's going on the power grid side. Yesterday, Professor Luis Carlos already talked about the energy transition and the 3D. He talked about 4D. I have a slide on 3D. Next time I will update my slide. The slide was ready. But the idea here that I want to convey is to show that energy transition will require grid system, the economy electrification, and this is tightly related to the power grid. We have to update power grid planning and operation in many ways, right? I will try to present here a few applications on how we're trying to upgrade this power grid. I'll start with some context. Then what is the potential future of the power grid? And two applications of different types of measurements. Nowadays, we have more difficulties, more challenges with intermittent generation, with higher loads of electric vehicles. So we have to adapt, but we also have much more data available through smart meters and through power quality meters. So how do we work with this data to improve grid operation? So I will not go into the details of the 3D. I believe you are already very familiar with the concept. What I would like to draw your attention is to the need for deep electrification. Decarbonizing the economy, electrifying a few processes, electric mobility, renewable generation with higher intermittency. We all need to improve our grid, to improve how it's planned and how it's operated. So the utilities here, I want to highlight, they have a key role in this transition, in my opinion, right? And they have to adapt. There is a significant need for new data analytics techniques to extract information from the smart meters, from the available infrastructure that we have in the modern grid. Okay, so what is the main transition, the main upgrades that we are observing? Traditionally, the power grids, especially distribution systems, they are very much planned and operated based on the worst case scenario, right? You didn't have enough data, you didn't have enough information, so why not planning it based on the worst case? And utilities have done this over the past decades. It has been working well. But now with the increased complexity of the grid, with intermittent generation, electric mobility, power electronic-based devices, it changes a little or a lot how the grid is operated. And we cannot operate anymore based on the worst case scenario. The worst case scenario may be too difficult to identify, too complex because the system is more complex, it has many more variables. So we may be unable to identify this worst case scenario, or even if we identify, it can be such an unlikely scenario that is not worth planning and operating our system based on this case, right? So we will move towards risk-based methods, statistics-based methods, AI, to process the data and try to identify likely scenarios, right? Based on risk analysis. I truly believe risk-based assessment is becoming more and more necessary for a proper grid planning and operation. So my idea here today is to present a few applications that are out there that we are developing, we have been developing over the years, and there's still significant need for newer and more applications for all this available data. Because we are having increased amount of data, but this data, they have inconsistencies, they have issues. Utility databases, they are updated based on manual processes, so it's prone to errors, right? So if we don't process, if we don't include some intelligence on the data, we'll not be able to extract proper information, okay? I will divide the applications in two parts. The first part, I will talk about applications of smart meters, which is one type of meter. In the second part, I will talk about applications on power quality meters, which is a different type of meters that provide more data, waveform-based data with higher granularity. This one has less granularity, but we can still identify many applications for this data to improve system operation. I have listed many here. I will not go into the detail of all of them. This is just for you to get an idea that we have many areas to cover, many areas to apply smart meter data to improve grid operation. For example, few examples. We have non-technical loss detection. This is about a project that we conducted with Canada, with BC Hydro in British Columbia of Canada, to detect non-technical loads using smart meters installed on the customers, on the low voltage customers. Basically, you extract this data and you process it in a proper way. I will not get into the details. If you want more details, we can discuss about it. But if you process in a proper way, you can identify non-technical losses based on using active and reactive power and voltage measurement with 15 minutes, 1 hour resolution. You also have other applications such as fault location. Nowadays, utilities are still, at least in Brazil, at least in our scenario that we work, utilities are still very much reliant on customer calls to locate, detect, and locate faults in the grid. If you have smart meters all over the grid, you can get this data, process it, and detect and locate these faults. You can also model the load. We know that specific loads, they may have different types of models, but modeling an aggregate load at the medium voltage or low voltage system, it's important for the utility to know how to plan its circuit. When is the peak load? What is the peak load? How does it behave with under voltage variations? This is important information for the utilities to plan and operate their system. And with more measurement, we can get this information, okay? Another application here, Professor Luis Carlos has worked extensively on load disaggregation. You can monitor the customer, and the customer can understand its consumption in different types of loads and improve your consumption, right? So, and there are many others. DER hosting capacity, system condition monitoring. If you have increased amount of data, you can predict failures in the system. Because a failure in a transformer or in a capacitor bank or in a cable, it does not happen suddenly. It starts sending you small signals, small signatures. If you watch the voltage and current waveforms, it starts creating distortions for weeks or even months before an actual failure happened. So if you are monitoring, if you are analyzing this data, you can avoid failures in the components of the systems, right? I'll give a little bit more detail about this application on smart meters that is updating and correcting errors in the utility database, right? As I said, the problems here with utility database, they have terabytes of data. And this is based on manual data registration. They are not always updated. And we also know that line and transformer parameters, they can change over time due to weather conditions and aging of the devices. So there's a huge problem here because we have large data. Utilities take all their decisions based on this data, right? And this data has inconsistencies. So if we do not process and understand, detect the issues and remove them, utilities will take wrong decisions, right? And this could be dangerous. It wasn't dangerous in the past because utilities were operating on a worst case scenario with a large safety margin, but it's becoming smaller and smaller, the safety margin that we have nowadays, right? So it's important to use this data, and we can use it, we can improve it with smart meter data. It's possible, for example, to correct system topology, line and transformer parameters, customer phase connection, status of switches. It's possible to detect and correct in the database using smart meter data. So here's an example of a work that we developed. If you have smart meters on all low voltage customers, you can do all these applications, which is first, topology and phasing correction. Many times the utility database the topology is not updated. The circuit goes under reconfiguration all the time. And sometimes the database is not updated correctly. So you can help correct this database based on the measurements of voltage, active power, reactive power measurements all over the grid. You can also detect tap changes in the transformers. You can detect capacitor bank status, whether the capacitor bank is connected or not. There are situations we are aware of where the capacitor bank is disconnected. One phase of the capacitor bank remains disconnected for weeks, months, and the utility doesn't even know because it's not monitored, right? With this monitoring, with these smart meters, we can detect this status. And also, it's possible to detect control settings of voltage regulators, controlled capacitor banks, based on 1 week of smart meter data with 1 hour resolution. You can change the resolution. Of course, if you have higher resolution, you'll get better results. But with 1 hour, 2 hour resolution, it's still enough to get good results. So this is a very important application. It will help utilities update and correct their databases. Based on my experience, this is a huge issue for utilities because they have such large databases based on manual processes. So getting proper information, reliable information, is a huge problem. And it didn't used to be a big problem because they used to operate on worst case scenarios, but nowadays it will become more and more important to keep these databases up to date. Moving on to the second application I would like to discuss, it's about using power quality meters. When using power quality meters, the difference between smart meters is that they have much higher resolutions. They capture the actual waveforms, right? So they're installed in less locations. They're not installed all over the place, but they still have they still provide very important information. If used properly, can be very, very useful. For example, you can detect, as I said earlier, signatures that a cable is going to fail, right? If you can anticipate this, you'll be able to avoid a big outage, right? And the IEEE, in fact, has recognized the importance of this area and established this working group on power quality data analytics since 2013. This working group has been going on for a decade now. It has worked and developed many applications. One of them, I'll just show a little bit of all the applications. We'll not go into the detail of these applications. But you can have system-based ones that you will analyze, anticipate problems in the system, in the power system as a whole, right? For example, fault location, fault anticipation. Here I'm talking about the whole system. Resonance analysis. If you have power quality meters installed in the grid and you process this data properly, you can identify these issues. The challenge is the data analytics, is how to process the data, how to understand the data, right? And you also have the component-based monitoring, where you can detect the operating conditions of capacitor banks, switches, transformers, lines. And you have load monitoring and modeling as well. So if you have this power quality meter data, you can more or less understand almost everything. I used to joke with that it's not really a joke, it's true, right? You can monitor from individual devices to wide area systems, literally from the big generators to the end customer loads. It's possible to monitor, it's possible to analyze their operating state, that operating condition, and anticipate failures, anticipate issues. This data you can use with RMS. You can even detect some of the issues can be detected with RMS data. You don't need waveform data, but some of the issues really need waveform data, such as capacitor monitoring, cable failure. It's important to use the waveform data, right? One application here is resonance analysis in wind parks. Recently, we have been experiencing many issues related to resonances, unstable resonances in wind parks. It has become an issue more or less around 2009, a decade or 15 years ago, with some problems in the US and in China. Here I have some sample events that happened. In the US, 2009, this wind park subsynchronous currents reached 4 per unit in less than a second. Subsynchronous voltages were 2 per unit in less than 3 seconds. So very fast events and very big events, right? Unstable oscillations that caused damage to the wind generators, to capacitor banks around. In China, they have a wind park complex that experienced these events, 58 events of unstable subsynchronous resonance in 2012, 2013, over a 1 year span. So it's more than one event per week, right? So this is really happening. One of them, I'm not getting into the details, but one of the main issues behind it is the integration of power electronic-based generators, right? They have some issues with resonance damping. They can decrease resonance damping, and that's why sometimes the system becomes unstable. And it's essential to detect these events as early as possible. The power quality meters, they allow us to do that, to detect as early as possible. And we developed the work where if you take measurements on the transmission line close to the wind park, this voltage and current measurements here, waveform voltage and current measurements, it's possible to process them and extract the subsynchronous component. This is only the subsynchronous component. This is the raw measurement. It's hard to notice the oscillations. You can notice a little bit here on the current. But after field processing, simple data processing, you can extract the subsynchronous component in one cycle and detect the event and disconnect the generator to avoid further damage, right? So this is very interesting. You have a lot of data available. You can do many applications with this data, right? The challenge is, how do you understand this data? How do you extract this information? We have actually developed this report on the IEEE working group. I was part of writing this report. It provides many signatures, waveform signatures, of how underground cables, overhead lines, transformers, switches, capacitors, they tend to show before they actually fail, right? So the report even got an award from the IEEE that it provides many signatures on how the equipment, they start to fail, right? And finally, if you want more information about the resonances in wind farms, there's this PhD thesis. There is a link for it. We also got an award here for this thesis. It talks about resonances in different types of wind parks, different types of resonances, and how you can detect and mitigate these resonances based on measurements, on power quality measurements at the point of common coupling, the PCC. And with this one, I conclude my presentation. I just want for you to, I would like to convey the message that we really need grid electrification, grid improvement nowadays. And due to the uncertainties, variabilities, unpredictability of demand and generation nowadays, we are moving towards risk-based methods, right? Instead of only analyzing worst-case scenarios. So we need more data analytics to properly identify these methods. We can have different types of measurements, smart meters, power quality meters. We need to develop applications for this data. And if we don't, we'll have bad data. And taking decisions based on bad data is even worse than making decisions without any data at all, right? Thank you very much.
Thank you, Ricardo. Maybe we have time for one question.
Thank you for a very nice presentation. I was wondering with your slide with the transformer station, where you were talking about the monitoring, but you talk about the smart meters. So it was not clear to me, you know, have you instrumented the transformer also with the sensors for measurement, yeah? Or do you indirectly make a model of the transformer state based on the data you collect from the smart meters?
Yes, it's indirect measurement. We have smart meters on the customers only, okay? So if you have these meters only on the customer, it's possible to indirectly estimate voltages and other parameters on other parts of the grid.
I think that leads to much more questions, so I think we will need to take them in the coffee break.
Yes, for sure.
So I'll make sure you don't run away.
Okay, I'll be around.
Thank you so much.
Thank you very much.
Professor Luis would like to ask a question.
Congratulations, Ricardo. Very nice presentation. Just would like to ask you to explain a little bit what kind of methods and algorithms you are using to improve the database from the distribution utilities.
Okay, it can come from various types of algorithms. Our area of operation is to try to start with the simple algorithms. What do I mean by simple algorithms? Calculate voltage and current trends over the year, extracts average results, standard deviations, and go on from that. But this is more on the smart meter side, right? For example, this application here from the smart meters, we use linear feet of data, how the data is changing during one day, and you add linear feet to this data to try to collect the topology of the system, right? This is some type of basic statistics. We use state estimation as well. If you can use state estimation over the year, over the day, for example, you know the status of the switches, how they change over the day, right? And if we go to measurements, waveform measurements, for example, cable monitoring, what we do is we extract again RMS data from the measurements. This RMS in cable failure, for example, you will see on the result that it keeps jumping. The RMS data keeps jumping when the cable starts to failure. So we tend to start working on this basic analytics, right? It's not the idea is to start from the basics. If we don't find solutions, we look for other techniques. Okay, thank you.
Thank you very much.